Structural Components, Part 2, Construction. Using a case study test building outfitted with non-structural components and systems and constructed at the National Science Foundation Shake Table facility at the University of California, San Diego. A full-scale, 5-story building was built and tested at the Engelkirk Structural Engineering Center at the University of California, San Diego, and equipped with non-structural components. Specific topics that will be discussed include the construction of the columns, shear walls, beams, and floor slabs. The first objective is to provide an overview of the conventional construction strategies for columns in structures. The second objective is to offer an overview of the conventional construction strategies for shear walls. The third objective is to introduce the conventional construction strategies for beams in structures. And finally, the fourth objective is to explain the conventional construction strategies for floor slabs in structures. Typical foundation structures are built below ground. Because this experiment was conducted on a shake table, the foundation was constructed above ground. Therefore, some differences from conventional foundation construction practices will be highlighted in this video. One of the most apparent differences between the 5-story building case study and footing construction in conventional buildings is that the test building was constructed directly on a shake table, also called a steel platen, rather than on the ground. This table, found at UCSD, is an outdoor shake table with a one-direction axial loading feature. Missing in this video is the initial step of excavating the earth in order to place the foundation into the ground. When constructing a specimen on a shake table, the test structure is cast directly only to the top of the steel platen, requiring formwork to support the sidewalls of the foundation. In the field, however, shallow footings can make use of the natural sidewalls provided via the excavated earth. But formwork in the field is required if the sidewall of the foundation extends above the natural grade or ground level. Vertical longitudinal bars provide the concrete with increased tensile resistance to axial loads or flexural loads, which are due to out-of-plane bending. Transverse hoops or spirals provide confinement of the concrete core, help prevent buckling of the longitudinal reinforcement, and also provide shear strength to the column. Rebar cages, in general, also control shrinkage in the concrete, which will be induced due to internal temperature fluctuations in a concrete member. Therefore, the reinforcing cage can delay the onset of cracks in the concrete. The cross-section of reinforcing cages can take any shape based on the complexity and aesthetic factors for the member being constructed, from circular to any other shaped polygon such as squares or rectangles. In this project, the columns were rectangular, and therefore the longitudinal bars were placed in a rectangular cross-section with transverse ties being provided up the height of the column at a constant spacing. Typically, reinforced concrete columns are detailed such that a nominal amount of cover concrete is provided between the edge of the cross-section and the reinforcing steel. This concrete cover is measured from the outside face of the column to the first longitudinal reinforcing bar and based on American Concrete Institute standards. Concrete cover is used to protect the reinforcing bar from environmental effects such as water intrusion, which may cause corrosion, or to protect against extreme situations such as fire, both of which would weaken the steel reinforcing bars. After installation of column rebar cages and completion of pouring the foundation concrete, formwork for the shear walls and columns are installed simultaneously. Formwork is the general terminology used to describe the temporary mold into which the material is poured into, in this case concrete. In the construction of the columns and shear walls, the formwork is often erected on-site from prefabricated segments which are constructed off-site. In this example case study building, the formwork for the shear walls was installed first. Both sides of the shear wall require formwork to support the wet concrete, while the top of the formwork is left open to facilitate placement of concrete. The formwork for the 4 columns at the corners of this building is installed in a similar fashion. The shear walls in this building were designed with the same shape throughout the height of the building, aligned vertically, and supported on a deep concrete footing. This type of consistent configuration from floor to floor results in repeated use of the wall formwork, increasing construction efficiency. Once all formwork at a given floor level is secured, the structure was ready for pouring the concrete. Concrete is a composite material composed of 2 or more different materials mixed that when combined produce an even stronger material. In the case of concrete, it is composed of aggregate and cement. Aggregate is either fine or coarse-grained, with material sizes ranging from fine sand to gravel or, at its largest, crushed stone. Using a range of aggregate sizes within the concrete mixture provides an inexpensive void filler and further reinforces and strengthens the overall composite material. The typical mix proportions when making concrete is 10 to 15% by weight cement, 60 to 75% aggregate, and 15 to 20% water. These proportions are varied until the desired workability or ability to flow is achieved. One way to assess the workability prior to placing the wet concrete is to conduct a slump test on site. In a slump test, a cone-shaped mold is filled with wet concrete. A metal rod is inserted into the top of the cone and pumped up and down 25 times. This helps eliminate air bubbles and increases the homogeneity of the concrete mix. The cone is then lifted slowly and placed adjacent to the free concrete that is allowed to slump down under its own gravitational weight. After the slump settles, the metal rod is leveled horizontally on top of the cone, and the distance from the horizontal rod to the top of the concrete is measured. The change in height of the concrete sample is referred to as the slump for that specific batch of mix. The slump measurement is compared with specified values, and a decision is made to accept, modify, or reject the concrete mix before placing the concrete. In the 5-story building construction, once the desired concrete mix was attained, the concrete was poured into the formwork using the truck-mounted boom pump method. In this method, a wireless remote-controlled robotic arm, called a boom, is used to assure accuracy of the concrete placement within the formwork. Immediately after the wet concrete mix was poured into the formwork, the concrete was vibrated to eliminate voids or air pockets. The top surface of the concrete was then screeded to assure it was level and smooth, as well as bring near-surface water to the top of the concrete. A screed is a flat board, often made out of wood or metal, used to smooth the concrete after it has been poured. This process is done to extract the excess wet concrete and ensure that the top surface is smooth. After pouring and finishing, the concrete was left to cure for a few days until it was fully hardened and the formwork was removed. After the concrete in the columns and shear walls on the first floor were cast and cured to sufficient strength, the construction of the second floor began. First, the necessary formwork was installed, and then reinforcement for the second floor beams and floor slab were placed. Concrete beams and floors, just like columns, need to be reinforced in both transverse and longitudinal directions. In this 5-story building test, openings in the floor slab reinforcement were provided in order for the staircase and elevator to be installed, as well as service pipes. Reinforcement around these penetrations through the floor slabs was more concentrated due to the fact that there would be higher stresses surrounding the openings. After placing reinforcement, the concrete was poured and the surface of the floor slabs was screeded to level and smooth them, just as was done with the shear wall and columns on the ground floor. The construction of the upper floors more or less followed the same procedure, with the formwork being reused up the height of the building in order to construct each of the primary structural components: the columns, shear walls, floor slabs, and beams. In this video, the primary structural components needed to carry vertical and lateral loads of a building are discussed. These components consist of columns, beams, shear walls, and floors, each of which must be well detailed and interconnected to ensure a continual load path from the roof to the ground level of a structure to ensure its stability. Finally, an overview of the conventional construction strategies adopted for these components when using poured in-place reinforced concrete as the construction material is presented via a case study building construction example.